Hey everybody, today we're talking about the second derivative test for local extrema. We're going to get the big idea and we're going to get a relatively non-computational example. In the next vid we'll get down and dirty with the algebra behind it. So let's start with an example. Here's a picture. Here I have drawn a graph that has critical values at x equals 3 and x equals 4. You've got a local max at x equals 3 and a local min at x equals 4. Notice at x equals 3, the graph is concave down. The slope of the tangent line is decreasing as you read from left to right. And that's where we have the local max. Similarly, at x equals 4, there on the right, where we have the local min, the graph is concave up. The slope of the tangent line is increasing. As it turns out, this is completely universal. So suppose that we have a function that has a critical value at x equals c, such that the derivative of the function is 0 at that point. So it's a special sort of critical value. Then the second derivative test says that if the second derivative is negative, then f has a local maximum at that value. If the second derivative is positive, then f has a local minimum at x equals c. However, if the second derivative is exactly 0 at that critical value, then the test doesn't give you any information. You have to use some other technique, usually the first derivative test. One warning about this, you have to be really careful to only apply this at critical values where f prime is 0. If you try and use this test at some place where the derivative isn't 0, you're going to get results that are meaningless. So watch out for that. One brief example, here I'm giving you a function and its two derivatives, so we're not actually going to compute those here. F of x is x squared over x minus 3, and I've given you the derivative and the second derivative. Find and classify any local extrema. So the first step is to find critical values, and just looking at f prime, I can see that I'm going to have critical values at x equals 0 and x equals 6. X equals 3 will also be a cut point, but it won't be a critical value because it's not in the domain of the original function f. So those two critical values, x equals 0 and x equals 6, each get plugged into f double prime. Once I've figured out where the derivative is 0, I can take those values, see what the sign is of f double prime for each one of them. At 0, f double prime is negative, so by the second derivative test we have a local maximum at x equals 0. At x equals 6, the second derivative is positive, so we get a local minimum at x equals 6. We can see this on the graph. On the next slide, we should see a maximum at 0 and a minimum at 6. And in fact, we do. At x equals 0, we see we have a local maximum. The value of the function is y equals 0. And at x equals 6, we have a local minimum where the y value is 12.